Great. Thanks for coming, Suda. Thanks for inviting me. Yeah, so this is kind of, right, so I'm Michael Dinitz. I'm an associate professor here at Hopkins. This is kind of a very quick, very brief intro to problems I like, problems I care about, stuff I've been thinking about these days. I should be able to kind of see the chat and, feel free to kind of ask any questions. Okay, so yeah, this is theory of network design. Right, so I work in theoretical computer science. I'm a theoretical computer scientist. And, I think there's a wide variety of backgrounds of the people here. So I'm going to kind of do a wide variety of different levels of abstraction. So what is theoretical CS? This is where we use mathematics to understand computation and objects relevant to computation, as I'll talk about in a minute. And, for some people, if you haven't seen this before, this is a little bit counterintuitive. Computer science feels like this very applied thing. I write code and my computer does what it does. But there is a whole theory behind it, and that's what I work in. And in some sense, you could think of this as the opposite of computational mathematics. Right? So in computational mathematics, which is this super fascinating area, we use computation. We do kind of experiments on computers to understand mathematical objects. Okay, so here, instead of using computation to understand mathematical objects, we're using mathematics to understand computational objects. There's a lot of different parts of theoretical CS. So I've just named 6 here, but there's a ton. I work mostly in algorithms. So that's this thing, but I dabble in most of these. And the thing that unites these different parts of theoretical CS is that, like I said, we're using mathematics to understand computation, right? So we're proving things. We're using all the formalities that you know and love from your kind of theoretical math classes, but we're just doing it about computation rather than about purely mathematical objects. Okay, so this is kind of a one-slide overview of some of the stuff I like, some of the stuff I'm interested in. So I like to work on computationally difficult problems. Right, so that's this first column. I like to deal with NP-hard problems, which some of you may have heard of. So these are problems that are kind of provably hard to solve if you take a couple things as assumptions. We deal with that in many ways. The way I like to deal with it is what's called approximation algorithms, which I'll talk about in a minute. But the main idea in approximation algorithms is that, I have these hard problems. I can't solve them because they're NP-hard. So what I'm going to try to do is get close to optimum. But I'm going to prove that, right? So again, to contrast this with practice, I'm not going to kind of write some code, test it out on some instances, and kind of argue that it tends to work well, right? I'm going to kind of define my problem, formally define my algorithm, and prove to you that all the time, this algorithm is pretty good. It's close to optimum. A lot of the problems I care about are graph algorithms or problems on graphs. Oops, problems on graphs. So it's the second column. So I'll talk about those in a minute. And again, probably most of you here know what graphs are, have seen them before. These are sometimes also called networks, right? So this is just, I have a bunch of nodes, I have a bunch of edges between them, and I want to kind of do things on these graphs. So I'll talk about those more in a minute. And then, because I do like to do applied stuff, every once in a while, I work in kind of distributed computing and the theory of networking. So this is third column. So things like how to design data centers, how to design overlay networks, how do you do reconfigurable networking, what about some wireless network stuff? So all of these have theoretical components that I've worked in and I'm interested in. Okay, so let's talk about network design a bit more specifically, because that's what I kind of promised in the title. Right, so you can think about this as I give you an input graph. So I'm giving you some graph, and I want a subgraph that satisfies something. So I'm going to do some examples of this in a minute, but there's kind of 2 flavors. So one is optimization and one is existential, right? So you can think of like, here is the input. Find me the best thing you can on it, right? That's an optimization question. Or you can think of saying, for every input I give you, I can always do something pretty good, right? That's an existential guarantee. So these are complementary in kind of nice ways, right? Like, what's the point of optimization? If sometimes there aren't subgraphs that are any good, then why do I care about finding the best one, right? Like, who cares if they all are bad? Okay, on the flip side, if I prove to you that there's always some subgraph that's pretty good, you pretty naturally want to find the best one, right? So then you get the optimization. Okay, but that's all pretty abstract. Let's see some examples. Right, so minimum spanning tree. This is probably like network design problem 0. This is the one everyone starts out with in their first theory of algorithms class. Right, so here I give you this graph. That's this thing over here on the right. Some big graph sitting here. And I say, find me the subgraph, which is connected and spanning. Right, so it's spanning. It needs to touch all the nodes. And it's connected, right? So I can walk from any node to any other node. And my notion of best here is minimum total cost, let's say. Right, so for example, if you look at these green edges, hopefully you can see some of the edges turn green. Right? Like you can see this is a spanning tree, right? So every node is touched and the whole thing is connected. And if you think of the cost of an edge as like the length and the way I've drawn it, maybe you can convince yourself this is the minimum way of doing this. Maybe it is, maybe it isn't. I didn't actually check, but okay. I think this is the minimum spanning tree. Great. Right, so this is a network design problem, right? I gave you a graph. I said, find me a subgraph, find me a network that has these properties and is as good as possible. Right, and so again, a theorem that probably many of you have seen in your kind of algorithms 101 class is that you can solve this problem. Right? We have very famous algorithms that compute the MST, Kruskal's algorithm, Prim's algorithm, Boruvka's algorithm, there's a whole bunch. So we can do this, which is cool. Like this is a very useful task. It's useful in practice, useful in theory. Okay. To contrast this, a different thing that we might want to do is talk about what are called spanners. Right? So a T-spanner is a subgraph which preserves distances. Right? So in any graph, I have a notion of distance, which is just the shortest path between two nodes. And I can say, find me a subgraph that preserves the distances up to a factor of t. Okay, this is a useful thing to do. Here, I think these green edges form a 3-spanner. So I think you can convince yourself that any two nodes, their distances is preserved up to a factor of 3. Okay, so for example, originally this node and that node are at distance 1, right? There's an edge between them. Right? And now in the green edges, I have a path of length 3, right? 1, 2, 3. Okay, so all the, and that's for this pair, but I claim this is true for all the pairs. Right? So I preserved all the distances up to a factor of 3. Right? So this we have an existential theorem for. Right, as opposed to the optimization theorem from the MSTs. This says that for every integer k, I can always find you a 2k minus 1 spanner with n to the 1 plus 1 over k edges. It's just like, this is always true. This thing always exists, and I can always find it for you. Right, so for example, if you want a 3 spanner, so k is 2, right, then I can give you one with n to the 3/2 edges. If you want a 5 spanner, so k is 3, I can give you one with n to the 4/3 edges. Just like always true, an existential result. Okay, right, so this is 2 kind of quick examples of network design. And I claim that, this theory of network design is important in both practice and theory. So I'll just say kind of this is my very biased point of view on it based on the applications I care about and the kind of stuff I've worked on and the kind of problems I like. Right? But you can imagine, right, I'm building graphs. Right? Building graphs are like building networks. Right? So this is like tons of applications in networking and distributed computing. Right? So we use what are called expander graphs or finding expander graphs to build data centers. So that was in this Conex 15 paper. So that was a network design problem. I've done it on building overlay networks on the internet. Oops. So that was this ICDCS paper. I've done it for building smartphone peer-to-peer networks. Right? So all of these different networking tasks kind of have somewhere in them a question of find me a subgraph that has some nice properties. Right? And that's the kind of problem that I like to attack. It's also used in high performance computing. These are what are called preconditioners for linear systems, turn out to be a really nice network design problem that I'm not going to go into. And they're just used all over the place, right? So in surprising places. So I've kind of told the story a bunch recently because it kind of just happened, but we've been hiring this year at Hopkins in computational biology. I think it's, we interviewed a bunch of people. It's a very cool area. It's an area I don't know much about. I'm not a biologist by any stretch of the imagination, but I was helping interview these people and had a really cool conversation with one of them because it turns out that this one particular network design problem, the so-called Steiner tree problem, turns out if you could compute Steiner trees for some type of genomic data set, this led to some cool biological insights that I really didn't understand, but sounded very neat. So this shows up even in places you might not expect. And they're also kind of super important theoretically, right? So this is actually kind of a lot of my motivation, is that these are kind of just super classical problems. These are one of the first set of problems that we thought about when people started really designing algorithms systematically in like the 60s and 70s and the 80s. And they're a test bed for new algorithmic ideas. So kind of a huge fraction of like the good algorithmic ideas that have ever been come up with were kind of originally developed in network design problems. Not all, but a huge fraction. So they're a good test bed. Okay, so I've worked on all sorts of these things. Let me kind of maybe not go into them. Good. What am I working on these days? Because again, like these are kind of stuff I'm actively thinking about. So if anyone is interested in these problems, like I'll say at the end, feel free to send me an email or get in touch. I've been thinking a lot lately, the last year or so, about what's called relative fault tolerance. Right, so this is the idea that I want to design something that's fault tolerant, but I want it to be relative. Right, so, okay, what do I mean by fault tolerant? Let's think about this classical absolute notion. Right, so an obvious notion of fault tolerance, if again I put maybe my networking or distributed computing hat on, right? Like this graph is maybe modeling a data network, right? Like think about the nodes as servers, and these edges are like links that go between these servers. Okay, like edges fail, right? And nodes fail. Like this happens. It's unfortunate, but it happens. I don't know how many of you kind of saw this kind of news, but I guess it was all over my Twitter a couple of days ago. I guess in the most Canadian story ever, up in British Columbia, a beaver chewed through a fiber optic cable and destroyed the internet to some small town in British Columbia. Which, like, again, you need to be fault tolerant to beavers eating through your cables. Okay, this is a thing that happens. Okay, so what if some of the vertices or edges fail? Right, so one obvious notion is what's called the k-edge connected spanning subgraph problem. Okay, so I give you a graph and I say, let's suppose that k things fail. I want you to still be connected afterwards. Right, so like the minimum spanning tree says that 0 things fail, right? I just want you to be connected with what I give you. But now if you maybe look at the green edges in this picture on the right, you can kind of convince yourself that if any one edge fails, this is still okay. If any one of my green edges goes away, everything's still connected, and that's nice. Right? But if 2 edges fail, that's not true anymore, right? Like, for example, if these 2 edges fail, I can isolate that node. Right? There's not a whole lot I can do about that, right? Like my graph only has 2 edges at that node, so if those 2 edges fail, I'm kind of stuck. Okay, so that motivates the relative fault tolerant question, which says, sure, like I'm stuck if these 2 edges fail. Right? If these 2 edges fail, I'm stuck, nothing I can do. Right? But if like that edge fails and that edge fails, I'm not stuck, right? Like I could kind of have bought this edge down here, right? And then I'd be okay. Right? So the relative fault tolerant notion says that if these F things fail, so if any 2 things fail, then this green set of edges that I've bought still have the same connectivity properties, more or less, as the kind of original graph that I gave you. Okay, so, okay, here I'm not going to kind of go into too much detail, right? But if I add in these 3 orange edges, now this is 2 fault tolerant, 2 relative fault tolerant. So, I mean, this sounds like a small change, but it's actually pretty dramatic. This changes things kind of quite a bit. I've been working on it a lot lately. So with one of my PhD students, Amma Kurenteng, we recently developed basically, it's called the 1 + 4 over F approximation algorithm for this problem. So, okay, again, not going into details, this is a short talk, but more or less, we have pretty good ways of solving this problem, even in the relative fault tolerant case, which is significantly trickier than the absolute fault tolerant case. Okay, you can do the same thing with spanners, right? So remember the definition I had of a T-spanner was that all distances are preserved up to a factor of T. right? So what I have written here is kind of the formal way of stating that, right? And this green thing on the right is this 3-spanner that I built a few slides ago. And I can change that to be fault tolerant, right? And to say that if F things fail, then the distances in my graph minus failures and my spanner minus failures is the same up to a factor of t as my distances in the original graph minus the failures. So, okay, again, not going through the details, not too much time, right? I can add in maybe these, 5 extra orange edges, and this is going to turn into a 2 fault tolerant 3-spanner rather than a 0 fault tolerant, which is what I had originally. Okay, so this sounds kind of technical, and I don't certainly expect you to read all the math and understand the details here, right? But the point is that these are network design problems, right? This is saying I give you a graph, and I want to find a subgraph that has some nice property, and the property I care about is that even after faults, I'm doing okay, right? And doing okay, the difference between relative and absolute is that in relative fault tolerance, doing okay means I'm doing like I am in my original graph minus failures. Whereas absolute just says like, I'm doing okay, kind of absolutely, not relative to the underlying graph. Okay, and there's a notion of vertex fault tolerance versus edge fault tolerance. I'm not going to go into. I've been working on this a lot. Here's just 2 tables I snagged from 2 of my recent papers. And you can kind of see like, we got these existential bounds. I care about the size and making it small as a function of kind of the number of faults and the stretch and all these things. And, we care about the running time. We can do this for vertex fault tolerance and for edge fault tolerance. You get different bounds, a whole bunch of different algorithms. There's a lot going on. Okay, that's all I want to get out of this slide, is that there's a lot going on. Okay, and you can get kind of fun algorithms with fun bounds. Okay, so just to finish up, right, there's like this notion of relative fault tolerance sounds like a small change, but I want to be fault tolerant relative to my underlying graph. Turns out to be kind of surprisingly new and have a bunch of open questions. Like here's a bunch of open questions about kind of connectivity, about other objects, spanners. Okay, right? Again, all I want you out of this slide is that there's plenty to do. Right? What we're doing is we are designing algorithms that we can prove using formal mathematical tools, give us the objects we want, and are fast. Right? So that's what we do. Okay. Right, so if you're interested in any of this, check out my webpage, send me an email. Like I said, like hopefully what you got out of the last slide is that there's still a whole bunch of stuff to do. I'm actively working on it. And I should say, in this slide, Robel, who's the co-author on both of these, is a undergrad, actually not from Hopkins, an undergrad from UMBC, who based on we wrote these 2 papers, and now he's going to be in the fall starting his PhD at MIT in theoretical computer science. So you can write papers and you can go to grad school and do this stuff. Okay, thanks.